So welcome everybody. It's a pleasure to have Dr. Qu Zhu here today. Thanks a lot for accepting our invitation. Dr. Qu Zhu is a Kavli Institute for Particle Astrophysics and Cosmology Fellow at the SLAC National Accelerator Laboratory and Stanford University. He obtained his PhD at the Kavli Institute for Cosmology and the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge, UK, where he studied CMB lensing measurements with ACT under Professor Blake Sherwin in 2023. He is a member of ACT, DESI, and the Simons Observatory, where he is the co-leader of the L3 working group. His research interests include CMB lensing autospectral measurements and cross-correlation of CMB lensing with galaxy surveys, as well as secondary anisotropies. Today, he will talk to us about cosmic structure growth through the lens of the CMB. Frank, thank you. Take it away.
Thank you so much, Jackson, for the nice introduction, and it's thanks for the invitation. It's great to be here and talking to you. Yeah, so today I'll be talking about the view of cosmic structure growth through the lens of the CMB. A lot of the work that I will be presenting is done as part of the ACT collaboration, and the ACT is a collaboration with about 160 members spread over 45 institutions. Here's a picture of one of the last face-to-face meetings we had back in 2022. And a note that today I'll be focusing mainly on the CMB lensing results that came from ACT. Just have a quick advertisement that we also recently had our latest CMB primary data release, and all the information such as the papers and the likelihoods and the notes about how to use the notebooks can be found here. So I encourage you to have a look. But today we're going to focus on using the CMB as a backlight. So here is an outline of what I'll be focusing on today. So first, I'll give an introduction about what CMB lensing is. Then I'll be mainly talking about the results and all the robustness and challenges that we faced with doing lensing with ACT, and telling you about the cosmology constraints that we get with these measurements. And finally, I want to show you the what further improvements we can expect in the sciences of CMB lensing. So just to start and motivating the things, I'm sure that many of you know here that there is a large amount of information about our universe found in the distribution of matter. And to a good extent, we understand how structures form under gravitational collapse over billions of years. We can simulate them very nicely, as shown here in these kind of simulations from Francisco Villascusa. And what is really interesting is that how the structures forms and how they get distributed over time, that it depends sensitively on things such as the composition of the universe, what is the underlying theory of gravity, and how the density perturbations evolve. And therefore, understanding or trying to map the mass distribution enables us to understand some of the key properties of the universe. In particular, one key parameter that we're interested in is how clumpy this structure is. And this is usually parameterized by sigma 8. So this is kind of motivates why we want to make these direct, precise maps of mass, and in particular dark matter, to higher precision. And one of the things we can do when we do these measurements of mass is to create these very powerful but agnostic tests of our cosmological model and ask questions such as, do structure growth behave as expected from the standard cosmological model? And the way we would do this is to fit at early times, for example, the lambda CDM model to the CMB, to the observation of the CMB at redshift 1100, and then predict how this structure grows under the assumptions of standard general relativity, the standard components of the universe, such as the lambda CDM, and predict how the structure will grow and clusters at later times. And then we can contrast these kind of predictions with these direct measurements that we can do with things like gravitational lensing of galaxies, and in this case of CMB. By comparing these predictions and observations, this is a really powerful stress test of our understanding and of the lambda CDM model. And any sort of new physics will show up in these kind of comparisons. So we should be doing this more and more often with higher precision measurements, this so-called SA tension, in which the CMB-based predictions lie slightly higher than some of the direct low redshift measurements made from this kind of galaxy shear measurements. So these predictions here shown in green from the CMB are shown here. The direct measurements from galaxy measurements here are on blue. And while none of these are measurements by itself are excessively significantly different, it is interesting that a few of them, many of them are around 2 to 3 sigma low. So the question is whether there is a problem with the lambda CDM model. Is this just we are unlucky with some statistical fluctuations, or whether there is some systematic effects creeping in one or these probes? So doing this direct measurement has been very interesting in recent years. And today I'll be focusing on adding a new observable on the low redshifts, which have independent systematics to galaxy lensing, which is using the CMB directly as a source. So the CMB is really a very nice source and well-behaved source to study gravitational lensing. And that is for a few reasons. So first, we really know the redshift origin very well. We know it's a single plane at redshift 1100. We also understand its statistical properties very well. It is mainly sourced by linear physics, and we have mapped the CMB to exquisite precision throughout the years. But perhaps the most important reason that this is a nice source is that it is the further we can really see. And therefore, it's probing all the mass distribution as the CMB photons travels towards us. So how do we measure what is the key observable that we are after? The main observable is the lensing deflection field, which we mainly represent by the gradient of the lensing potential phi. And what this observable is telling us is essentially the direction from which the CMB is emitted to where it's ultimately received. And here I'm toggling between simulations of lensed and unlensed CMB on a patch of a few degrees. And you can see that this deflection is a very subtle effect. That's about the small Archimedes-sized deflections. But the reason we can really observe this is that this is coherent over the degree scales. That's kind of the sizes of the dark matter clamps causing the deflection. So this is the main observable that kind of maps the CMB from where it's emitted to where it's ultimately received in our telescopes. How do we go to measure it? In a nutshell, we use this algorithm called the quadratic estimator. And that estimator basically takes into account the changes in the statistical properties of the CMB G2 lensing. And we can understand that from the real space, the unlensed CMB is translationally invariant. However, under the presence of a fixed lens, that breaks kind of this isotropy of this unlensed CMB and introduces like new mode couplings that in Fourier space, it means that before translation invariance means that two different Fourier modes are uncorrelated, but due to the presence of lensing, you induce kind of these new couplings modulated by the lens phi. And the way we can measure this effect is basically doing a mode-by-mode reconstruction of the underlying lensing field by taking quadratic products of the CMB maps filtered in a particular way to measure this correlation. So by exploiting the modulation of the small-scale CMB due to the large-scale lenses, we can obtain a reconstruction of this mass map. And here is an example of this reconstructed mass map from the CMB. And in order to do precision cosmology, what we do is, as usual, take the power spectrum of this lensing map. Naively doing that, we get these lensing power spectrum. So this is after subtracting a set of biases that is common in this kind of lensing reconstruction process. But what this is showing here is on the y-axis how much lensing you have as a function of the angular size. And you can notice it peaks around an L of 60. So this exactly corresponds to these degree-sized lensing cramps that causes the deflection. You may also notice that this shape is pretty familiar. In fact, the reason for this is that this inherits its shape from the matter power spectrum, since it probes the lensing probes the distribution of mass in projection, as shown here. And therefore, CMB lensing will be sensitive to many interesting information cosmologically that affects structure growth, such as these kind of things like combinations of sigma 8 and omega matter, and in physics that affects growth in general, like neutrino mass. So the goal of making CMB lensing measurements is to add a measurement at low redshifts that can provide an insight on how structure grows. And CMB lensing have completely different systematics to galaxy lensing measurements. And with ACT, what we hope was to provide a measurement around the 2% level on these key parameters informing of growth, such as sigma 8, omega matter to the power of 0.25, S8, and sigma 8 in general. And they all have completely orthogonal systematics to galaxy lensing, and as well as to the measurements of Planck CMB lensing. So that is why these measurements deemed to be interesting. In particular, it's worth noting that when we are talking about these measurements of S8 or sigma 8, all these different measurements are sensitive to different regions of the parameter space. And what CMB lensing is really good at is to provide really detailed measurements of structure growth at high redshifts and large scales. So these kind of measurements all complements really well in understanding where how structure growth at different scales and redshifts. Okay, so having probably hopefully motivated why CMB lensing is interesting, I will move on now to discussing the lensing measurements done with the Atacama Cosmology Telescope. And this is done in collaboration with some of the key members in this group shown here. So first, I will just introduce ACT. ACT was an augmented resolution telescope located at the heights of the Chilean Atacama Desert. So it is located in a very dry area at high altitudes for these microwave measurements to do these very precise measurements of the CMB at high resolution, which is what we really need for lensing. I say it was a telescope because ACT has been dismantled to give way to Simons Observatory that I'll discuss a few more details at the end of my talk. But what ACT was really good at is producing these very high resolution CMB measurements that we can use for measuring lensing. In particular, you can see what ACT really adds is this really small scales and high resolutions where you can even see the individual galaxy clusters by themselves in blue dots like here and the AGN in red. And it also provides a lot of high resolution polarization measurements. So what we do for lensing is to take these temperature and polarization maps and run that through the quadratic estimator to provide to produce these kind of dark matter maps. And so this is what we did. And we turned these CMB maps into signal-dominated lensing mass maps covering a quarter of the sky. Because it is really signal-dominated, what we are seeing here, these blobs are really structures of dark matter at a particular direction of the sky showing projection. This is really also a step up compared to space surveys like Planck. So the map produced here, it really has twice the signal to noise per mode compared to Planck, which has a larger footprint, but the noise levels are just much higher. So most of them, what you're seeing in the Planck map will be noise, but here, this is kind of the real structure. We can zoom in to this dark matter map a little bit more. So here I'm plotting the gravitational potential. And again, in this patch, what you're seeing here, these bright regions are regions which have a higher distribution, higher clumpiness of the dark matter in this particular direction. And what is nice with this kind of maps is because they are signal dominated, you basically don't need to take the word for me that what we're seeing here is real dark matter. So what you can do is to pick another tracer that follows the dark matter distribution very well and filter it in the same way as this map and overplot it, and hopefully you can see close correspondence between them. One such tracer is the CIB, the cosmic infrared background, that has a similar redshift dependence around redshift 1 to 2. That this is the infrared emission given by dusty forming galaxies. And what we can do is to take these measurements from the Planck survey and overplot them as contours here. And hopefully you can see the clear resemblance where areas of more dusty emission galaxies corresponds to the peaks of where we measure the lensing distribution. So perhaps it's not really surprising that the luminous matter traces the underlying dark matter distribution, but with these kind of lensing maps, we can really showcase that. So back to a bit more concrete cosmology, perhaps I want to say that the main challenge of the lensing measurements done with ACT is not how to make the lensing spectra or the mass map, but due to the high resolution of the measurements, we really want to see like how can we robustly measure the signal at the 2% level to obtain a robust measurement. So doing the quadratic estimator, we have been doing that routinely since the past, but the real challenge is how do we trust this very high resolution measurement? And one thing good with this ACT is that it provides a lot of redundancies in which we can make detailed checks of our data. So we have a huge level arm to really stress test over our measurements to make sure that the signal is robust. In particular, we have followed like a blinded analysis procedure where we have never looked or compared our measurements with theory before we pass a series of tests about the things that we are potentially worried about. So here is just a flavor of this kind of 200 notes we did. So namely, the things we care about are we passing all the foreground tests? For example, are things consistent between the polarization and the temperature channels? Different estimators designed to pick up or be immune to different foreground contaminations. Is our signal isotropy on the sky? So because of the large footprint, we can do detailed tests between different patches of the sky. Are we passing the symmetry test? So this, if you're more familiar with galaxy lensing, this is like the B mode tests. We can also isolate the signal using different scales of the CMB. These are all done here. And finally, we did a comprehensive check and understanding of instrument-related tests. For example, do we understand the noise of our maps, whether different arrays of the experiment give the same signal, whether the different temporal observations also give the same signal. So there's a long array of tests we can do. And I won't bore you with the details, but if you're interested, I will just highlight some of the key challenges that our measurement have to overcome. So the first one is whether our measurement is safe from the contamination from extragalactic foregrounds. And the problem with foregrounds is that the CMB that we measure, that we pass through our quadratic estimator, not only contains the CMB, but also contains other effects that are interesting on their own, that, however, for our case, are considered as foregrounds. And this includes the cosmic infrared background, the thermal SZ effect, and the kinetic SZ effect. So these are all folded into the CMB that we measure. But as you can see here, when we pass through the quadratic estimator, the first term is what we want, but these other terms are also correlated and with the underlying dark matter distribution. And if we don't mitigate them, they can induce these kind of foreground biases that could bias the results, especially when we are after like a 2% level measurement. So Neil did a very careful check of the extragalactic foregrounds to make sure that they are under control. And this is kind of based on a three-pronged approach. So first, we test the impact of foregrounds using two different sets of simulations, and where we add all the realism similar to what's done in the data, make sure that the bias inferred there is very small. However, we don't want we also include new estimators such as profile hardening that kind of estimates the 4-point function induced by the foregrounds and project them out, as well as other foreground mitigation strategies, making sure that they give similar results. So these are like frequency-dependent approaches and geometric-based approaches. And we test them both on the simulations and also on the data, where we have a lot of data-driven tests where we can play with combinations between the frequency channels, such as 90 and 150 frequency channel, to ensure that these foreground biases are really small and our results are not only dependent on the simulations, but also are consistent results with the data. So this is an example shown here, showing the consistency that we are unbiased by foregrounds, where we pass in through the quadratic estimator by using these CMB difference maps between the 90 and 150 GHz channel that that do contain different levels of foregrounds. And the fact that the difference doesn't pick up any signal, it shows that we are not sensitive, or current methods have already mitigated the foregrounds well enough. And this is also backed up with the simulation-based tests showing that the level of foreground is small. Another challenge with our measurement is because we are doing this measurement using ACT on the ground. The noise modeling is very complex. And here what I'm showing is the scan strategy done by ACT and the 2D noise power spectra of different regions on here. So the takeaway here is that the noise have a lot of structure, and it really depends on the location, and therefore it's very anisotropic, and hence very challenging to simulate the noise properties properly. However, we did a very good job here in providing robust noise models that captures the details of the scan strategy and the interplay with the atmosphere. So as a comparison, you can see the 2D noise of Planck is much well behaved and doesn't have so much structure. Despite having these very improvements in noise modeling, we really want in lensing to be robust to the details of the noise modeling. And that's why we use these kind of cross-correlation based lensing estimators. And the motivation for that is that when we just use the standard quadratic estimator, when we are training these very simple tests, where we basically just passing signal node map, so differencing two different CMB splits, such that the map we pass through is just noise only. On passing that through the noise only, passing that through our lensing estimator, rather than getting something consistent with 0, we're getting these kind of consistent U-shaped failures, and we suspect that was still due to some failures in the noise modeling, where we are seeing still something propagate to the lensing estimator. So the solution for that is to use this kind of new cross-correlation based estimators, where we pass through 4 independent CMB splits measured at long with long enough separation, temporal separation between them, so that the instrumental noise between them is independent, and therefore really making our measurements immune to these kind of noise modeling issues. And by doing that, we see that we go from this kind of failing null tests to these passing ones. So this has been an issue that didn't allow us to pass the null test for a long time when we were starting this project. By using this, ensures that we are really robust to the details of our instrumental noise. So the key in here is having these robust foreground mitigation techniques, such as profile hardening, plus these cross-correlation based estimators, means that we start passing all our null tests. And here is just a summary of a flavor of them, where we test comprehensively a set of these things, really elevating our measurements, making it robust, where we test, where we get consistent results. So this is parameterizing our lensing measurements by these amplitudes, showing that the difference of these measurements at making this measurement at different times, using different polarization channels with different foreground cleaning strategies, with different frequency channels, using different patches of the sky with different scales. They are all consistent within 0, within the measured uncertainties. And some of these tests are really challenging to pass because we are canceling out the signal. Therefore, they expect these errors to be very small. However, using our robust estimators, we're able to pass this set of tests. And it's really adding to the robustness of these measurements. Okay, so having hopefully walked through the challenges with CMB lensing and what we can do to mitigate them, now I will move on to talk about the cosmology results using CMB lensing. So here is our measurement shown in red. And you can compare that with the prediction based on the Planck 2018 CMB cosmology shown here in black. So they agree very well with each other. And it's worth pointing out that the black curve here is not based on a fit, but just purely a prediction, a theory prediction from the CMB itself. And therefore, showing that without needing to marginalize any nuisance parameters, we get these very good agreements. And this lensing amplitude is measured at the 2% level. It was one of the highest signal-to-noise CMB lensing measurements to date, and has a very good PTE, passing PTE of 17%. So in terms of structure growth, the lensing measurement from ACT really agrees well with the CMB predictions. Here is trying to put a bit more our measurements into context. So this is the evolution of the field through the perspective of ACT itself. I think this has been a really rapid progressing field from just a direct detection happening in 2011 with ACT to these kind of precision probes around 10 years later, where we can say detailed things about structure growth and cosmology. And this is thanks to the improvements and all the work done in the field by all the different measurements from ACT, Planck, SPT, and others shown here. So this is a rather basic plot, But I think the main takeaway here is that because we are after the same observable, the lensing field, it's very easy to compare all the different experiments by plotting them on the same graph. Hopefully you can see that all the measurements are very consistent with each other, and that the ACT result here is one of the one with the highest scale to noise. So there are also recent measurements here by SPT here in blue, and they are all very consistent with each other, as well as Planck. As well as Planck here shown in purple. So all these measurements, they are very consistent, and this is a very fast progressing field with a lot of exciting results to come in the future from the ground-based surveys, as I will show later with the work done with ACT and also with Simons Observatory. So in terms of cosmology that we get from our lensing measurements, we measure this combination S8 CMB lens, which is basically sigma to the omega matter to this exponent here, which is this direction that we constrain best. So here we show the whole sigma omega matter contour from our measurements. And again, you can see that this measurement is really consistent with these kind of early time CMB predictions, not only from the Planck 2018 here in orange, but also with other alternative data sets such as ACT DR4 plus WMAP, and the same with the ACT latest DR6 CMB anisotropic predictions. What we can do as well is we notice that our measurement is very consistent, not only with the CMB predictions, but also with Planck M-pipe lensing shown at the back in the gray contours. So what we can do is to combine these two measurements at the likelihood level to achieve even more constraining constraints. And this is shown here in red, where we captured all the correlations that exist between the two surveys, although they are very small because one Planck is a space survey and ACT is on the ground, and because there are two different instruments, they have different instrument noise, and they cover different patches of the sky and are dominated on different scales. So therefore, the combination is very constraining and also consistent with the individual measurements. So we get even better constraint on S8 at the 2.2% level that is also consistent with the primary CMB. So the conclusion on the lensing auto-spectrum perspective is that lambda CDM is well behaved on large redshifts and large scales. And can we say something about going to even lower redshifts? The way that our ACT measurement is designed is that it has a large amount of overlap with different existing and future surveys. So it's really useful, and I already started a large amount of projects and synergy with cross-correlations with different surveys. So for example, we can do cross-correlation with galaxies, quasars, Lyman alpha, and CAB. But I won't go through all of these measurements in detail, but just want to highlight a few of them using galaxy cross-correlations to show that things are also seems to be okay on this lower redshift area and also large scales. So one of these measurements using ACT is a cross-correlation between the overlensing map and the UNWISE survey. So the UNWISE is a galaxy survey covering the full sky, and it mainly have two redshift bins, a green one around redshift 1.1 and a blue one around 0.6. While I won't go through the details of the analysis into much detail, so in this analysis led by Garrett, what we did is to do these cross-correlation tomography measurements that enables you to measure structure growth at even these kind of lower ratios of 0.6 and 1.1. And the story here is very compelling. So this is summarized in the plot here, where one is the prediction from lambda CDM. So here we're plotting the ratio of the sigma 8 we measure against the Planck predictions. And you can see in the perspective of ACT, the structure growth behaves as expected from the lambda CDM model, both at the outer spectrum level, C alpha phi, extending down to these low redshifts. So there have been a lot of activities in these areas based on these cross correlations. I definitely won't do justice in just having one slide, but here is a summary of some of these surveys extending to even lower redshifts than the one on Y zone here. So here's just an example showing measurements using the DESI legacy sample here in orange, and the spectroscopic LRG shown here in gray. And the takeaway here is that the fit, for example, of these legacy sample cross correlations also agrees very well with the lambda CDM predictions. And that in the perspective of ACT and these cross correlations, lambda CDM seems okay at lower ratios as well. And it's really complementary to these measurements at smaller scales from galaxy lensing. Talking about tensions or data can also provide insights on the Hubble measurements in two different ways. So the first one is the more standard one, that adding CMB lensing really helps to provide tight constraints on H nodes, where, for example, the BAO plus the BAN measurements are here in blue, but the lensing measurements are basically have a degeneracy orthogonal to the one from the BAO itself, and therefore the combination of lensing and BAO, calibrated BAO, provide these very tight constraints here in red that's consistent with the early time predictions, again, of Planck CMB here in green. But perhaps what's interesting is that we can do also these alternative measurements which is not based on the scale of the sound horizon of the baryon drag epoch given by the BAO, but using a different scale coming from the matter equality scale, which is imprinted in the matter power matter distribution the lensing is sensitive to. And this is a very good cross-check of whether there is recombination physics can alter the values of H nodes. And these measurements provide the following, shown in these contours here, which is also consistent with our primary CMB measurements. So while this is still not too competitive compared to the probable CMB or LSS, this is also a very interesting null test that we hope to do more and more in the future. Finally, CMB lensing also can constrain help in the constraints of neutrino mass sum, where by combining with the CMB anisotropies, which predict the low, we can predict how the structure suppression due to neutrino mass, and compare that with the primordial power spectrum to constrain the effect on neutrinos. And with our previous measurements, we were already reaching these pretty interesting constraints using both BAO of 0.13 electron volts. And the takeaway in these results is that CMB lensing with ACT does help a bit compared to just having Planck lensing, but also probably not, this is not appreciated that much, or in that lensing does in fact help in constraining neutrino mass by adding that to baryonic BAO. So here is a case where we don't include lensing but only have BAO, but adding a lensing does significantly improve the upper bound. So I'm sure a lot of you are aware with this interesting upper constraints using ACT CMB lensing, ACT Planck CMB lensing, and with the Planck ACT primary CMB, and DESI year 1 BAO from ACT, the latest results from ACT, and also with the latest DESI collaboration ones that also use the ACT and Planck CMB, that gives a very tight constraint on the neutrino mass. So we are really moving into this very interesting regime. So while I won't say much about this, I feel like there's like a lot of interesting activity happening on this front, trying to understand the power of the different data sets. Here's just a summary of where you can get all of the products and likelihoods. They are all available on Lambda. So I encourage you to play with kind of this or our measurements. They're all in the likelihood. And if you want to do cross-correlation analysis or all the maps and combinations of the maps and simulations, they're all found online here. Feel free to reach out if you have questions on that. So on the remaining part of my talk, I would just want to show what does the future provides in terms of mass mapping with CMB lensing. So here is again a reminder of the measurements we have done. And broadly speaking, you can separate that into two regimes. So first, we have this cosmic variance limited regime, where the only way of improving the measurements is by having access to a larger scale area. And we can see, and then there's the noise limited regime. So here we are showing the ACT reconstruction noise per mode. And you can compare that to the Planck measurements. So you see that we are single dominated up to scales of 150, but there's still like rooms to improve with future data on this noise limited regime by having more optimal measurements. And I kind of want to illustrate some of this here. So here's our current noise level that I shown in the previous slide, but there are a set of improvements that we are really working hard towards achieving. So first of them is in terms of including data, we expect to have to use our daytime data, and that should add 1.7 amounts of data. And there's also an additional season of the nighttime. And in terms of optimal methods, we hope to use more optimal filtering, improve the sky cuts, and add map level combinations with Planck, so at the CMB level, to then access better lensing reconstruction that way. In terms of more data, we expect the additional nighttime season that we haven't used to improve our signal to noise by 12%. And the daytime data, we hope to gain an additional 30% in terms of the signal to noise. So there are just a lot to gain in terms of using the data. However, using data daytime is challenging due to the trying to avoid the sun and having different systematics from the beam, and a lot of worries about the instrument or heating up and stuff like that. However, we have been passing some encouraging null tests. So here just showing some of them where we pass in a map level, a map where we difference the nighttime CMB by the CMB taken at the day. And passing that through our lensing pipeline, we obtain consistent results with null. So this is very encouraging, showing that we may be able to use the daytime results. So Irene is pushing very hard on this front, passing through all the null tests and hoping to add the daytime data in the mix. In terms of the more optimal methods, we hope to have improved sky cuts. So shown here in red is the current baseline measurements, but we hope to be more aggressive, and there have been work done. We have been doing work in showing the impacts of galactic foregrounds, and it seems that we are able to go to a less restricted mask here in light blue, and this should improve our signal to noise by around 20%. And combining them with these map level combinations with Planck and better filtering of our CMB maps that we pass through the quadratic estimator, we hope to obtain signal to noise between 60 to 70 in the next final set of analysis with ACT. So I hope you stay tuned with that. And finally, I have mentioned that the site where ACT was has already been dismantled. to give way to Simons Observatory, and that's something that a lot of members of ACT are very excited about, to work with these kind of experiments. So that's already showing first lights and taking data with the LAT. So this is going to bring CMB lensing to an even higher regime. So here is the forecast from the ASO collaboration a few years ago, showing that we would expect a signal to noise of conservatively around 140. So this is really bringing lensing to these sub% levels of regime to really do stress tests of our understanding of GR and the lambda CDM. And any kind of physics that affects structure growth will show up in these kind of measurements. Similarly, we expect this kind of very competitive bounce on the neutrino mass. So this is also some forecast to look up to. So this is kind of all from me, and I can just leave you with the conclusion. So in the perspective, from active perspective, if you want to ask the question of, do we understand structure growth? It has to be a resounding yes. So here I'm actually even showing the summary, the Planck Act CMB. I agree very well with these late time measurements that we do with ACT. And it's also interesting to point out that the latest results seems to be back of concordance, where the kids' legacy and DES 3 measurements are also showing up on the higher side, agreeing with the direct predictions. Yeah, so that's all from me, and I'm happy to take questions. Thank you.
Thanks so much. Very interesting talk. So, comments, questions? So, Laura?
Hi, thank you for the great talk. I have a question more about the modeling side, because you've been showing that the lensing data from ACT is so much better than what we had before, and it's gonna get even better, like even more better. So do you think there will be a problem from the modeling side? Because as far as I understand, what is used for nonlinear corrections is still based on the Halo model, so HM code and Halo fit. And
Yeah.
do you think that model reaches its limitations? And is it still good enough for current data, but will it like be good enough for future data?
Yeah, I think that's a very good question. I would say that, yeah, so for the current data, we are still using HaloFit. And I would say for the current one, and perhaps for a few more releases from ASO, perhaps like the modeling of whether using the like on the dark matter modeling is probably not the main worry, but maybe we need to consider a bit more careful in terms of the treatments of baryon feedback. So here's a plot of the lensing with and without baryons, and I think we're getting into an interesting regime for the future where we may need to worry more about this kind of the feedback models we use. But for example, there's also a recent analysis of CMB lensing that's sensitive a bit more on the nonlinear scales like SPT 3G, and there I think they have shown that the impact of having different dark matter models is fine. Like they're robust to different dark matter models. So I think it's even on the scales that we're gonna test, I feel like it's still gonna be fine for the next kind of measurements. Yeah.
Thank you.
Thank you. Meet?
Yeah, thank you for the very nice talk. I had a question. So in challenges, you mentioned that we are taking into account the thermal SG effect. Are we also taking into account the kinematic SG effect? I understand that it is quite harder to actually take into account, but is there any idea of taking that into account as well later on?
Yeah, so I think that's a very good question. So I think there have been papers looking at the potential biases of VKZ on these lensing measurements, and they they have shown this to be very small. And I think one of the ways to answer this question is that the KZ effects between on the CMB, it's gonna show up in even like higher CMB multiples that we are using for these kind of reconstructions of Lmax of 3000, and the KZ effect is gonna be is pretty small for what we want to measure. In fact, due to the filters and the stuff we use, and in fact, it is something that we want to measure at the 4-point level as well. So, but for that, we have to apply a really different kind of filters and stuff, and that's kind of dominated by other foregrounds. So I think this is going to be a very small effects on lensing. So I think the main piece is going to be like the TSZ clusters. Yeah.
Yeah, I understand. Thank you very much.
Okay. Any other comments, questions? Laura, yeah, Laura.
Actually, can I ask another very quick question? Like when you combine the ACT DR6 with Planck PF4, do you need to take into account correlations and covariance, or is
Yeah.
it at different scales?
Yeah, that's a very good question. So I said in the talk that we expect these correlations to be very small, but note that there is overlap between Planck and ACT, and some of the signal-dominated modes are going to contribute to this. Like we're essentially measuring this kind of same signal. So we do take that into account, and we basically rerun the same lensing reconstruction done by Planck by using the ACT footprint and the same filters by ACT to estimate this joint covariance. And overall, that correlation, we expect the same overlapping band powers to be around maximally 20% correlated, but that's taken into account into the measurements.
Thank you.
Yeah, Ross?
Yeah. Hi, Frank. Thanks for the nice talk. I was surprised that you didn't talk about any models of modified gravity, because the recent DESI data, they show equation of state that is compatible with possibly dynamical dark energy. So is there any part where you study that in the collaboration? And if yes, what are the constraints coming out from that?
Yeah, hey Peter, thanks for the question. Yeah, so dark energy, dynamical dark energy and things like this is very interesting coming from the DESI side. We did look at some dark energy constraints in Madavacheri et al. But my sense is that because lensing is the kernel is still like peaking at slightly higher ratios, the sensitivity on those lower ratios is not adding that much from the lensing side.
Okay, thank you. And so there's no way to see the data at the low redshifts and see if there is a hint of modified gravity, because now you integrate the whole thing. So that's why maybe from the low redshift you don't see any signal from dark energy, right? But if you look focused only on that part, you could see potentially, right?
Yeah, I guess. Yeah, you mean like more of like a tomographic approach of calculating that. So I guess one thing is the sensitivity of how much of the signal really contributes at those ratios. There have been cross-correlation measurements similar to the ones, let's see, I have shown here, like for example, the BGS sample, that's a really like in the dark energy dominated regime, and the structure growth there, for example, really follows as to the expectations from lambda CDM without invoking any alternative dark energy models. And also, I think I want to note that the latest ACT results, the 2-point function, they also combine, I think, with CMB lensing, and they're I thought that like it's not like slicing CMB lensing to the lower ratios, it's like the whole CMB lensing, and there it's not favoring any alternative dark energy.
Okay, thank you.
I think there was Owen and then Fotis.
Well, it was actually more just to follow up on that question. Yeah, it would be very surprising if you had a signal at the background level, like some deviation from lambda CDM, and we didn't see it at a perturbative level in S8. And now, like some of your cross correlations, you see in tomographic analysis, you seem to find that S8 varies with redshift, right? You haven't presented these results, but I mean, it's not unexpected if there is a genuine background problem, right? Do you have any comment?
Yeah, I guess, sorry, you mean it varies with background, like these kind of plots, like some of the measurements are like.
Yeah, so basically Saylor et al. From 2024 and Kim, this was like September, and maybe the later paper, was there a paper from October you led? Like,
Yeah, so we with these measurements, I think the takeaway is not that some of these measurements are low, or that, like, the interpretation has to be a bit more careful, that it's not that the essay there's a dependence over evolution. I kind of want to know that, for example, this value here is kind of only constrained by one band power, one data bin, so some fluctuation is expected. And if you look at the joint measurements provided by these three measurements, they agree with lambda CDM expectation, right? And same for I think the same is said for the Saylor et al. And Kim et al. Results. I think what the nice thing here between the orange and the gray is that slightly different data sets and different theory modeling gives you the same kind of consistent results. And I think the latest BGA's results really show that these kind of things, this kind of fluctuation, where if you kind of overplot what the low ratio looks like, it's kind of also agreeing with expectations, right?
right. Now, just to pick up on that, so if you look at F sigma 8 constraints from RST and you take like DESI, for example, like so what DESI's more or less shown is a high redshift, and it agrees with SDSS that basically F sigma 8 constraints are high relative to Planck. Now the question, and at intermediate values, it sort of agrees with Planck, and then at very low redshifts, there's a question, will they agree with peculiar velocities where basically F sigma 8 is a bit low? So you also see the same signal there as well, right? And you even see it in something like DESI, but DESI's low redshift stuff is a bit, like its constraints are a bit large. High redshift, it's fine. So there's a little excess relative to Planck. High redshift, intermediate redshift seems fine. And low redshift, there's a question mark.
Yeah, I feel like from like the kind of the latest BGS and stuff, it's kind of leaving less and less room at the very low rushes. But I agree that maybe there's a little bit of wiggle room there to see things, but I'm not sure of what kind of physical interpretation can happen like that. But yeah.
Right. Okay. Thanks.
Very good. Fotis?
Hi, thanks for your talk. It was very interesting. Just an idea. Can we put constraints on modifications on lensing from modified gravity using this data? So it is nice to use modified gravity to add terms in Friedman equations, perturbation equations. But a proper framework of modified gravity should have also modified lensing, in a sense. Is this something that people is working on or whatever?
Yeah, so thanks for the nice question. I think, yeah, we have looked at some simplest modifications of gravity in 3x2 point paper. I don't have the results here, but yeah, so those are like the things of including these kind of sleep parameters and stuff. Yeah, so definitely we can look at people have looked at those, and I think there are some other people for like DS results are also incorporating these measurements into those. And another interesting kind of thing on those lines I can look at is kind of these tests that these scale independent tests of whether GR is a good description is a good description. So this is kind of EG tests, and that has also been looked at in the ACT papers.
So let's thank Frank again. Thank you for such an interesting talk and also the Q&A. So